Today we will be discussing about the Lcr series circuit, that is the circuit which contains the inductor, capacitor and resistor in series. And consider such a circuit in which an alternating EMF is applied across the circuit and all these circuit elements, that is inductor, capacitor and resistor, are connected in series. We will try to understand the Lcr circuit using the Phasor diagram, which we have already discussed in the last class. So let VL be the voltage across the inductor and VC be the voltage across the capacitor and VR be the voltage across the resistor. Then we've already discussed in the last class the Phasor diagram of individual cases. That is, if we take the current along this axis, I represents the current, then voltage across the resistor VR is in phase with the current, which is given in the same direction. Since voltage is in phase with the current, it is represented in the same direction, that is VR. And voltage across the inductor VL leads the current by 90 degree. VL leads the current by 90 degree. Now again we had the voltage across the capacitor which lags behind the current by again 90 degree. So this is the voltage across the capacitor. Now we know that VL is greater than VC. We know that VL is greater than VC, which is why I have represented this by longer magnitude than the voltage of the capacitor, voltage across the capacitor. That is, the voltage across the inductor VL has greater magnitude than the voltage across the capacitor. For the reason we have discussed in the last class, that is VL is represented by IXL and VC is represented by IXC, and XL is given by omega L and XC is given by 1 by omega C times I. So from this it is clear that VL is greater than VC. Now which is why I have represented the magnitude of VL greater than the magnitude of VC. Now the equivalent or the resultant value of VL and VC will be in the direction of VL, since VL is greater than VC. So this will be VL minus VC. This represents the resultant voltage of VL and VC, which is pointed along VL because VL is greater than VC. Now we have to obtain the resultant between VL minus VC and VR, which will be given in this direction. So this is the resultant of VL minus VC and VR. So this is the EMF E, resultant EMF E. So the resultant EMF E can be represented by VR square plus VL minus VC square. And again VR is given by I into R square plus I into XL minus I XC square. This is E. So again taking I common outside, so this will be I square times R square plus XL minus XC square. Sorry, this was E square. So again current can be represented as E upon, taking this to denominator and taking the square root, E upon root over R square plus XL minus XC whole square. From Ohm's law, we can understand that this term in the denominator gives the effective resistance in the circuit, and this is called the impedance of the circuit. Impedance of LCR circuit. This is given by Z equals root over R square plus XL minus XC whole square. Now we know that XL equals omega L and XC equals 1 by omega C. Then Z can be written as root over R square plus omega L minus 1 by omega C whole square. So from this Phasor diagram, it is clear that the resultant EMF E, resultant EMF capital E, leads the current by some phase angle which is given by phi. Some phase angle given by phi. So from this figure we can write that tan phi can be represented by, tan phi can be written as this side, which is VL minus VC upon VR. So tan phi is VL minus VC upon VR. Again VL can be written as IXL, VC can be written as IXC, VR can be written as IR. So IXL minus IXC upon IR. Taking I common and cancelling out, we will get XL minus XC upon R. So this value of tan phi can be represented by something called impedance triangle. Impedance triangle, in which we have R in this direction, there is XL minus XC, and this is the impedance of the LCR circuit Z, and this is the phi. So tan phi equals XL minus XC upon R, and the resultant or the equivalent resistance of the circuit of the LCR circuit is Z, impedance. Now certain conclusions can be made from this equation. So in the first case, if XL greater than XC, if XL is greater than XC, tan phi is positive. That means phi is positive. Phi is positive means with this being the reference line and phi being positive, the EMF E, capital E, leads the current, which means this is an inductive property and the circuit is mostly inductive. Than being resistive or capacitive, the circuit is inductive. Circuit is more inductive. Circuit is more inductive. Now, second case, if XL is less than XC, what happens? XL less than XC means tan phi is negative. That means phi is negative. That means if phi is negative, it means it goes in the downward direction, which means the EMF E lags behind the current. EMF E lags behind the current, which is a capacitive property, and the circuit is more capacitive. Circuit is more capacitive. The third case, if XL equals XC, then tan phi is 0 or phi is 0. XL equals XC means XL minus XC becomes 0, which means tan phi is 0, which means phi is 0. Phi is 0 means E is exactly on this line, which means the circuit is purely resistive. There is no inductive or capacitive properties here. So, circuit is purely resistive. This third condition is called electrical resonance. We will be discussing about this topic in the next class.